Hi, everyone. So we're on lesson 6 today, I want to believe. So we're going to be talking about imagining complex numbers. In specific today, we're going to rewrite expressions involving negative roots using I, rewrite expressions involving imaginary numbers, and understand properties of the set of complex numbers. And this is our do now. On the left-hand side, we're just finding the roots. In other words, or finding the zeros, finding the x-intercepts. All those is the same thing. Setting these equal to 0, then finding x. That's all what that is, right? And this is, again, page 93 in your new Algebra 2 book, in volume 1, not volume 2. So it's supposed to be a V. So volume 1. If you look right here, we factored the first one. Again, if there are x's in two different places, either you're going to factor or you're going to use a quadratic formula. Those are the two options. That's all you got. For number 2, if you notice right here, we only have one x in one location, so we can just solve regular. You can, this is also a difference of squares, so you can actually do difference of squares with them, like with factoring. You can do it that way, but I think this just solving for x for me is a lot quicker. Same thing with this. This is in vertex form, right? It tells us the vertex, but that's useless to us right now because we just want to know what the roots are. So we're just going, and x is in one place, which means we are going to just solve for x. Please make sure you're adding 9 to both sides as opposed to square rooting first, because when you square root the left-hand side, when something is outside of the square root or outside of the square, you can't do anything with it. You just have to leave it like that. So what you want to do first is get the square by itself and then get rid of it. All right. That's why over here for number 2, that's why we added 25 first and then square root it. Same thing here. We're going to have to add 9 to both sides to get rid of the minus 9, and then we're going to square root it. Okay, we can't get rid of the 1 until we square root it because the 1 is inside the parentheses. All right, and so these are your answers. This is what it should be. And for number 4, if you notice, x is in 2 different places and it is not factorable. And so what you would do is use the quadratic formula. That is always your last choice. Once you're there, you can always do that. You can always use a quadratic formula. And if you notice right here, if you leave it as square root of 24, that's not going to be completely correct. I'm asking you to always simplify. You just get used to that, right? And then we notice 24, there is a perfect square in there. Perfect squares being like 4, 16, 9, 64, 25, things like that, where it has a number, right? And if I know that this is actually 6 times 4, right? 6 times 4 is 24. And that 4, what is the square root of 4? 2, right? And then what's left over is that 6, right? And so this is the way we had done it. Remember I showed you like the ladder way, reverse division way, upside down division way. Anyways, I still need to come up with a good name for that. Ladder way. Anyways, so 2 goes into 24 12 times, and then 2 goes into 12 6 times. I didn't continue on with 6 just because that doesn't have a perfect square in it. So I do know that 2 times 2 is 4, right? So that's how I got that. So there's the 2 and the 6. And from here, I knew that all 3 of these terms are divisible by 2. So we just -8 divided by 2 is 4, -4. And then 2 root 6 divided by 2 is just root 6. And then the 4 divided by 2 is 2. All right. We cannot simplify this more, even though you want to, right? Because you're like, 6 is even. That's not actually a 6. It's a square root of 6. It may look like a 6, but it's not. Okay. Because like the square root of 4, what's the square root of 4? Well, it's not 4, it's 2, right? So it's actually not, that's square root of 6 is 2 point something. All right. So if you look over here, from way back in the day. All right. So if you look right here, we wanted to know the roots, the y-intercept, the AOS, and the vertex, right? And we did that for all 3 of these. There's actually nothing really to calculate because we have a graph. It's already given to us. So it's just visual. You're just looking at it, right? And so we're like, okay, roots here, 5. So I wrote it as a point, and that's totally valid. So 5, 0. And then y-intercept, since I already stated that it's a y-intercept, I can just say it's 25. How did I get 25? Well, obviously it does not cross the y-axis anytime soon, right? And if you notice, well, they didn't cross yet. It's gonna be like way up there, right? And if you notice on here, on the equation, on the function, that this is plus 25. Remember, that tells us the y-intercept, right? So this is the y-intercept. If you don't remember, do you remember that? And then so, which makes sense because that's where it looks like it's heading. It's like way up there. And then our AOS right here is all that line of symmetry, right? Or what we call the axis of symmetry, which is always on the vertex. So I drew that in blue. And I tried to color coordinate it, but then I kind of lost in the in C when we got to C. And vertex is here at 5, 0. Notice you could have a point be a root and a vertex all at the same time. That's fine, right? And then if you notice right here, we had someone else ask about, well, what if it looked exactly like this, right? And here the 0, at 0, 0, it is not only the root, it is also the y-intercept, it is the vertex, which also contains the AOS. You see, it's like it did all of those things, right? It's multifaceted. And that is at the origin, that is the only place that will happen. It will not happen anywhere else, where all 4 of those things are related to that one point. All right. And here are the roots. Notice right here, I did not put parentheses around them, right? Because they're here at 0 and 6. If I put parentheses around them, I'm saying that this is a point. That would be wrong because that's 2 points. And since I stated that it's the roots, if you're just writing 0, 6, I don't know what that's for, right? But I labeled that this is for the roots and that's at 0, 6. If you wanted to write it down as 0, 0 and 6, 0, the only downfall to that is if you write that wrong, if you wrote this accidentally instead as 0, 6, that would be wrong. Okay, so that's the only disadvantage of writing it as a point. Y-intercept, since we say that it is an intercept, we know that it is, we're talking about the y value here. So that is just right here at 0. So here is the 0 is the root and the y-intercept all at the same time. The AOS is here at 3, but remember, we just can't say 3 because this is a line. A line is represented by an equation, right? Which is x equals to 3. So that's because this is where x is always equal to 3. Doesn't matter what y is. No, x will always equal to 3. That's why y is not even involved in here because it don't matter what y is. And notice vertex is written as a point. Why? Because it is a point. 3, 3, 9, right? So it's right above there, above the 8 right there, and we're going up by 1s. So yeah, 3, 9. So vertex always have to be written in ordered pair form. Readies? And then if you look at this guy right here, letter C. Here we'll talk about this part in a bit because we initially had said that this was, it didn't have any because it doesn't, right? And the y-intercept here is at 1. X AOS is that x is equal to 0 because that's where x is always equal to 0. That's the y-axis, right? And the vertex is at 0, 1. All right. We're going to move on. So this is the exact same graph as what we talked about before. This is actually in your Algebra 1 book as well. So for those guys who did not yet receive or did not receive the Volume 1 book, right? And you only have the Volume 2 book, sad days. It is in your Volume 1 book, page M5, 195. And actually all of your pages in that book are M5. So you just look for 195. M5 just means the module 5. That is the last module of Algebra 1, which nobody got to ever. And we won't get to this year either because, you know, things. And so if you remember right here, I squared is equal to, so we've defined, because when we're solving this problem of x squared plus 1 is equal to 0, and we subtract 1 on both sides, we're like x squared is equal to -1. You square root both sides, you're like, okay, happy, everything's good. But when the world is x squared, like what is the square root of -1, right? Because I know that the square root of 4 is equal to 2. Why? Because 2 times 2 is equal to 4. Well, the square root of -1, remember that we want it, what does it equal, right? Because what times what will give you a -1. I know the square root of 1 is 1, right? Because 1 times 1 is 1. But this one, you can't do that because so literally we've defined it as being I. Okay, so if I squared is -1, then the square root of both sides, so then I is equal to the square root of -1. Okay, so this is the definition of I. So if I ask you what so I never changes. That's why we don't use I as a variable, because I means something in math, right? So I is always equal to square root of -1. Well, then could we have like 2I? Yeah, so 2I, just like that. We'll talk more about that in a bit. right? And so now instead of saying, oh, we can't actually get this, we actually do know what these roots are. They're not real. They're imaginary, right? So what is the square root of -1? It is just plus or minus I. That is the answer. And that's why we set up here. I went too far. That the roots were plus or minus 1. That just means that, and we would never be able to graph it on here because you wouldn't be able to see it because it is actually not there. It's not a root on a real plane because these are all real numbers and I is not a real number. So we call these just imaginary roots. You just have to imagine. All right. So imaginary roots, anytime it does not hit the x-axis, we know that there are roots, they're just imaginary. Okay, now we can solve all the problems instead of just some of the problems. Because anytime we had like negative square roots, or square roots of negative numbers, we couldn't do them, and now we can. Happy days. So we call this imaginary roots or imaginary zeros. Okay, I underlined those guys. And we're going to go on a little bit. Okay, so I'm going to talk a little bit about this chart here. Okay, and if we're going to start at the bottom and go all the way up to the top. So back in kindergarten, we're going to do a little history trip here. So back in kindergarten, okay, this is what a lot of you guys dealt with, right? You did your natural numbers, 1, 2, 3, 4. And for many years in math, we just had these numbers, right? 1, 2, 3, 4, or whatever Roman numeral that you guys used, or that not you guys, that people used, civilizations used, or whatever Babylonian numbers, or what have you, right? Chinese characters, right? I know, I think a few of the Chinese characters for numbers, right? They're interesting. I just know 1, 2, and 3 really well because they're pretty easy. But natural numbers here, 1, 2, 3, 4, all the way to whatever, right? And then whole numbers, the difference between a natural number and a whole number is the addition of the 0. And they didn't have that for a long time because it's 0. Like, I want 0 fish, please. How much does that cost? Oh, that costs no money. Like, nobody's gonna have that conversation, right? So once we had 0 was actually quite revolutionary. I may have to tell you that one time. And then we get into integers, right? Integers, we maybe did that. You guys talked about that when we got to like 4th grade or 5th grade, maybe 6th grade. I'm not sure exactly when that is. But so that's all those integers from negatives to the positive. Now we have our number line, right? And the 0 is usually in the middle. And so those are the integers. And so then then we get into rational numbers, and rational numbers includes all this guy, right? Plus like the fractions and the decimals and all that kind of stuff, right? So not just any old decimal, but decimals that like can be turned into a fraction, right? Like for example, 0.75 is the same thing as 3/4, right? But anything that can't be written as a fraction, right? Because rational numbers are fractions, right? Anything that can be written as a fraction. All these numbers can be written as fraction. Just put it over 1, right? Are the irrational numbers. These are all the ones that are not rational, but they're also still real. So like, for example, the square root of 2, the square root, any kind of square root that does not have a perfect square in it, that's not a perfect square, is irrational. It is literally a decimal that goes on forever and ever, and it does not repeat. Okay, same thing with E, which we'll learn in second semester. Same thing with pi, which you guys should be familiar with, right? Pi 3.14159. That's all I know, right? So those are all irrational numbers. And then the rational, determining whether it's a rational or irrational number, it will determine, it will show up in the SBA, which some people are still taking or have to take. And so all this so far has been in the realm of real numbers. Okay, so we've been living in the world of real numbers. And then until today, right? Because today you are introduced to a whole new world, right? Of imaginary numbers. It's a whole different realm of numbers, right? Where nothing in imaginary numbers are real. I mean, they are real, but they're not in the real number world, right? They're imaginary. Okay, so there's so many word plays, right? So imaginary numbers are any like 3i, 2i. Notice we just indicated we didn't make a whole new like counting system for them. We just use this similar symbols as the real numbers, but we just put an I at the end, right? So technically this would just be like what I wrote here, a 1.5 square root of -1. Okay, so these all have to do with the square root of -1. All right, so even though we don't visually see the square root, that's what we're dealing with. Okay, so 3i, 2i, 1.5i. You could do even a fraction of 4/3 I, like, right, negative, it could be negative as well, but it is in now the imaginary number world. Now, when those two worlds combine, those two forces combine, right, what's going to happen? That's where we get our complex numbers. Always the real numbers first and then the imaginary number. Okay, that's just how we standard protocol. Okay, that's standard form. So that's why we have a real part here and then our imaginary part. And together that's called a complex numbers. So now you know all the numbers that exist in the world, right? The real and the imaginary coexist. So many things that I could talk about with that, right? So this is, if you notice right here, a plus bi, that's going to be your that's the common form, okay, where a and b are just numbers in the real number set. That's what I wanted to say. All right, so there we go. Moving on. All right, so if you notice right here, we're just going to rewrite them. So the long version, right, this is actually what's happening in, and this is why it works, is that the square root of -25, if you want to split that, if you split them up, you can separate it out to -1 times 25, because what is -1 times 25? -25, right? So we're going to separate them out. And then when we're multiplying two numbers and they're under a radical, we can actually just separate those two radicals, right? So it's square root of -1 and square root of 25. Well, we know what the square root of 25 is, right? It's just 5. So that's where this is right there. And we know that the square root of -1, it's been defined as I. So instead of saying square root of -1, we're just going to say I. So the answer is just 5i. What I like to do is I go, okay, I'm dealing with a negative square root, which means I'm definitely dealing in the world of I. So I write in the I. And then I go, well, what is the square root of 25? 5. So then I just write 5i. Okay, but that's why. This is the mathematical logic and reasoning for that. So if you look at this one right here, letter A, right, the square root of -4. Well, I know that this, if automatically when it's the square root of a negative number, I'm dealing with I. So that's I, and then the square root of 4 is 2. Just like that. Same thing with this one right here, the square root of -12. Notice right here that a -12, or that 12, I can reduce that down or simplify it down, or break it down, I should say. Break it down. There's two 2's, right? So that's going to be 2 root 3, because 3 is the one that's left over. And then I. So you could either write it like this, or you can write it where it's the I is next to the 2 outside of the radical. But if you write it like this, where the I, and you kind of make the mistake of extending that radical, that's wrong. Because what is the I? I told you that that was a square root, right? So it's a square root inside a square root. We don't want that. So make sure if you do it this way that you don't accidentally, oops, that's bad. Okay, you don't want that. All right, and then same thing for C. Again, you can write it this way, or if you want to write it in the standard form and be picky, like I'm not going to be too picky about that. You can write it, make sure just your I is outside of that square root. Okay, your pre-cal teacher might be picky about that, but I'm not too picky about that. Or maybe your physics teacher, upper level physics. But yeah, I'm not too picky about that. All right, and so if you look right here, and I said I would do this in the video, so here it is. So everything else looks okay. I'm just going to simplify this square root of -8. And so I know I'm dealing with I automatically. So here's my I, root. And remember 8 is going to be 2, and this is 4, 2 and 2. So I got 2 twice, right? Well, 3 times, but I can only use 2 of them. They only come in pairs. So I'm going to be like, oh, 2 root 2. So 2i root 2. So this leftover goes right here. These pair is going to be right there. All right, and then it's going to be divided by 2. Can I simplify this? Yes. Okay, if you divide a 2i divided by 2, is still, you can still do that. Okay, so this is going to be 6 divided by 2, which is 3 minus I root 2. Just like that. Okay. Now, moving on, and I don't know if you knew, but we can actually plot these things. So remember in class we talked about, or maybe you don't remember because you were not there, but that was not very many of you guys. It looks exactly like our X and Y, the coordinate a coordinate graph, right? Except here we have real. And so the x, what used to be known as x, we're calling that real. And our imaginary is our y-axis. Our y-axis is the imaginary axis. Okay, so we have the real axis and the imaginary axis. And we just plot them. So this is how we plot points, or a number, I suppose. It's not technically a point. But the number, so like 2 plus 3i, that's one number. So it's going to be 2, we go 2 on the real side, and then up 3 units on the imaginary side. So that's 2 plus 3i. 5 minus 3i, go right on the real number line 5, and then go down on the imaginary number line -3, right? 3 down, just like that, just like how we would with the order of operations, right? And so again, so this is going to be -3 and then 4i, so 4 going up. So personally, I would have you try some of them, do them in your book. I'm going to do a couple more. So let's take a look at C. So if you look at C right here, C is going to be 8, 6, 7, 8 plus 6i. That's going to be right here. So this is C. All right, and let's do D. Oh, what if it's just -6i? It's the same thing. It's going to be right there on that imaginary axis. That's our D. E is just -7. So we're just going to go on the real side, -7. Boom, right here. That's E. All right. And then if you look at G, H, and I, that I, there's a lot of I's going on. Remember this, we can just replace with I, right? So it's going to be 5 plus 3i. Just write it like that. Or this will give me -3i plus 3. Notice not in standard form, but that's okay because we know where to put that, right? So -3i, so we're going to go 3 negative, right? And then we're going to go +3 on the real. That's going to be your H right there. All right, same thing with this. It's going to be -4i minus 3. So -4i, oops. And then -3 right over here. So that's going to be your I. And notice right here, always for the I's, I put a little tail on it. And that's because I should be italicized. That's how we can tell if it's an I or like a number I kind of thing. Or number I, a letter I. All right, and not only can we plot them, but we could also add and subtract them and multiply them and all that kind of stuff. So this is in 6.4, which is on page 104. And if you notice right here, we just treat them like polynomials, like how we would with combining like terms. So you're literally like combining like terms, combining like numbers, I guess. So all the real ones. So I like to put them in standard form always. So I always deal with the real ones first. So 3 minus 6, which is -3, minus 1, which is -4, and then 4i plus i, which is 5i. So imaginary numbers and complex numbers have all the same properties of regular numbers, of real numbers. Okay, we just have to have that addition of I. And if you notice right here for C, we would just distribute like how we would normally distribute, and this is going to be 15i. And then 5i times -10i is going to be -10i squared. So what happens when it's an I squared, right? Remember we said that I squared is -1, because if we just take I and square both sides, right, we're going to get I is equal to -1. So instead of this being I squared, we have to simplify it down to a -1 like that. And then what is 10 times -1? Or -10 times -1, a +10, right? So this one I'm going to rewrite as in standard form. So it's +10 plus 15i. How did I know it was a plus? Because in front of the 15 is nothing. It's positive, right? So always your numbers is going to look like this. It will never have exponents, ever. Ever. If it has exponents, you didn't fully simplify that. Okay, same thing with this one right over here. What I like to do instead of having to write it out like this, because I'm lazy, I just cross out the I squared and then make that into the opposite of whatever it was. So if this was a plus, then I would just make that into a negative or something like that, right? Here, remember, you would just multiply out or distribute out the minus. So it's 3 plus 2i minus 1 plus 6i. And then 3 minus 1 is 2. 2i plus 6i is plus 8i. Right? Are we going to be testing on this stuff? No, but it's good for you to know because I want you to be ready for pre-cal. Right? I don't want pre-cal to be the time where you're like, Oh, shoot. I'm supposed to know this. All right, if you do something like this, if you take I minus 3i, I plus 3i, ooh, remember these are called conjugates? So let's try this out. So 1 times 1 is 1. 1 times 3i is 3i. This is minus 3i. And this is minus 9i squared. Well, I know that the 9i squared, so this is negative 1, so I'm just going to make that into plus. And then what do I have left? Well, my i's are kind of canceled out. My 3i minus, no more imaginary. This is 1 plus 9, which is just 10. So we started out with two complex numbers. We multiplied them, and we got a real number as a result. Weird. But yeah, it's because those i's cancel out in the middle. And then the one at the end, remember I squared. That's just, so that's how you would do those. And we're going to talk more about imaginary numbers on Thursday.